Hi, I'm Brent Waters, and I'm going to be talking about a new approach for non-interactive zero knowledge from learning with errors. So non-interactive zero knowledge proofs, or NIZICs, are a foundational primitive in cryptography, where we have a prover that wants to convince the verifier of an MP statement X and also has a witness W. And moreover, we want the prover to be able to convince the verifier of this in just one shot, where it runs the proof algorithm, produces a proof or certificate pi, and the verifier is able to verify and accept or reject this without any further interaction. And for any type such a system, we need two properties. First of all, we want it to be sound, where that the verifier should only accept if and only if X is actually in the language. And also we want it to be zero knowledge, where the verifier learns no information about the witness W. Okay, so the first really foundational work in solving this for NP languages was due to FLS in 1990, where they showed how to build NIZICs in two parts. The first thing was that they introduced this idealized model called a hidden bits model, where a trusted party would generate a random, would choose and generate a random string. Now the prover with this string could choose to selectively reveal some of the bits, but it's not allowed, importantly, it's not allowed to change any of them, and the remaining bits should remain hidden to the verifier. The second part was to build this to an actual construction. So this can be looked at through the abstraction of a hidden bits generator, where I want to be able to have a small commitment to an arbitrary, let's say, k number of bits, where my commitment size should depend only on the security parameter and not on k. Second, I want the commitment to be statistically binding for all outputs. You shouldn't be able to open it two different ways. And then finally, the unopened bits should remain computationally hidden. Now, if you want to look at the history of getting NIZICs from number theory, it's both very interesting and also very challenging. It's been hard to come by these things. The first instance we can look at is due to this FLS paper, where in 1990, they showed how to get it from the RSA assumption. And it wasn't until actually about 13 years later where Canetti, Halevi, and Katz showed a second number theoretic primitive, roughly getting it from bilinear maps, for which we could get NIZICs. This follows shortly on the heels of the Boneh and Franklin paper, showing, in some sense, introducing bilinear maps to the wide cryptographic community. Now, not too long after that, the Canetti, Halevi, Katz work did this from the hidden bits paradigm, and not too long after that, Groth, Ostrowski, and Sahai showed how we could also get more of a direct gate-by-gate approach to getting NIZICs from bilinear maps. And then finally, around this time, a third number theoretic primitive emerged. This was the learning with errors assumption introduced by Regev in 2005. And this gained a lot of popularity from the cryptographic community, both because it had nice properties, like, let's say, possibly being resistant to to quantum attacks, but also because it turned out that the cryptographic community really dove in and tried to build many different things from it. And over the next ensuing years, we could get all sorts of things, famously fully homomorphic encryption, but also identity-based encryption and attribute-based encryption for circuits. But also around that time, many people naturally tried to get NIZICs from learning with errors, but this turned out to be a really stubborn problem. And it wasn't until 2019 where the first solution emerged from two different works, let's say, combining together. And they showed how to get it, but surprisingly not from the hidden bits paradigm I just talked about it, but from something called correlation and tractability. And this was surprising, for example, to me, because if I had a bet, let's say earlier, on which model or say method would have led to this, this was rather unexpected for me. But what was remarkable also is that these correlation and tractability techniques led to many other interesting works like batch proofs, also, let's say, NIZICs from the decisional Diffie-Hellman assumption. So a lot of downstream good things came from it. But what I want to do in this work is kind of take a step back and also ask, well, it was great the correlation and tractability worked out, but why didn't the hidden bits model work? I really would have in some ways expected it to. And you might say, well, why do you ask why? Why take a look at this? Well, first of all, I care most of all about our understanding. Was there a fundamental barrier here? Or when we were looking at it before, was it just not being approached in the right way? Second, I think anytime trying to solve an interesting problem, you hope that technique, what happens a lot of the time is new techniques emerge, and we hope that these can be used to solve other problems. And I might expect that to happen here. And finally, care from somewhat of a practical efficiency point of view. Now, we won't, to give fair advertising, we won't get to practical efficiency, but one perhaps drawback of the correlation tractability work is that it had to make non-black box use of underlying cryptography. In particular, it essentially does homomorphic encryption, homomorphic encryption evaluation on other public key primitives, which could lead to some limitations in terms of practicality. And here we're going to be interested in, can we do it from black box use of the cryptography? So the result that I'm going to present here will be that I'm going to introduce a new hidden bits realization of NISIC from the learning with errors assumption. And so let's just dive right into that now. So first of all, I want to be a little more formal about hidden bits generators. Here there'll be a setup algorithm, which takes as input a security parameter lambda, along with an output length k, and outputs a common reference string. Second, there's going to be an algorithm for generating these let's see, just a second. For generating these bits. So this algorithm will output a commitment com along with k bits, R1 through Rk, and the respective proofs pi1 through pik. Finally, there'll be a verification algorithm which takes as input the common reference string, the commitment, an index I, a bit beta, and a proof pi, and it will essentially decide whether beta is a correct opening of the proof. So from any hidden bits generator, we're going to want to have 3 different properties. First of all, we want the commitment to be short. That is, should be polynomial and lambda, and in particular, independent of k. Second, we want it to be binding, or ideally statistically binding, where for any commitment and proofs pi, there should not exist proofs pi 0 and pi 1, which will open up a bit I to both 0 and to 1. It should only be able to open it up to 1 at most. And finally, we want it to be computationally hiding. That is, an attacker cannot distinguish the bit Ri from random if it is not given the opening for it, even if it's given the opening for the openings for every single other bit out there. Okay, now our solution will fall into what we call a dual mode setup. And this is kind of a common thing that happens in such a system, where there's 2 different types of setups I could do. The first setup, which I'll call hiding mode, will informationally theoretically guarantee that the hiding properties hold. There will also be a different type of way I could set up the parameters, which I call binding mode, which means that the soundness or binding properties will information theoretically hold. Now, clearly, these can't both hold at the same time. So what we have is essentially a bridge between them, which we want to be able to say, well, you can't distinguish whether my setup common reference string was a hiding mode or binding mode. And the bridge in this case will be built from the computational assumption of learning with errors. That is, if I'm given a matrix A of right dimensions, I can't distinguish a matrix A along with S times A plus some small noise from just A and a uniformly random vector. Okay, so let's first look at our construction in hiding mode. So in hiding mode, we'll have this setup algorithm, and the first thing we'll do is choose a prime q, roughly of size 2 to the lambda, and then pick lattice parameters n, and then m, which would be about 2 log of q times n, and then finally a parameter l, which I'll put here as roughly lambda times m times k. So the important point here is that L is much larger than M, and this will be important. Next, it's going to choose matrix U of in ZQ of dimension n by L, so very wide matrix. And then finally, for each I from 1 to k, we're going to sample pairs AI and WI, pairs of matrices, such that AI times WI is equal to U. But what's important is that we sample them where the entries of WI are small or short entries. Okay, and then finally, we're going to choose vectors V for all output bits, where VI would be just chosen to be randomly in ZQ to the M. Okay, so that's that for the hiding setup. Now to generate the bits, we're first going to choose what I'll call a seed. And here the seed is going to be really long. It's going to be of length L, and its entries are going to be not fully big, not fully in ZQ, but not necessarily fully short, somewhere in between, so about square root of Q type size. And our commitment is simply going to be to take U times T. And so what this is going to do is going to take our very long seed of length L and compress it into a much shorter length N vector. And then the way I prove things, the way I get my proofs for each individual bit, is I'll just take Wi times T, which will give a pi I be of length M. And then for the output bit, which will be this random vector that I chose from the common reference string, Vi times pi I, then I'll do some rounding to get a single bit out. Okay, now finally, suppose we have our verification algorithm. This is going to be done mainly by just multiplication matrices. So to check, the first thing I'm going to do is check that the commitment is equal to AI times pi, so that's just one multiplication. And then we just do the same evaluation and make sure that's equal to beta. So do the same evaluation that the gen bits algorithm would have done. Okay, and then finally, there's going to be one additional check. We want to make sure that our proofs, the entries aren't too big. So let's just say that that they don't have any entries greater than 2 to the lambda to the 0.6. Now, the first thing that's really important to check is that correctness happens. Okay, so suppose that I give the verifier AI times pi I. Well, the way pi I was constructed is it was just Wi times T. So I can make that substitution there. Now, remember from the setup algorithm, we had that all AI times Wi is equal to U. So I can make the second substitution, I get Ui times T, but that's just our commitment com. Okay, so that the first check then just works out. And the second check works out by the fact that Wi's were chosen sample to be really small, and the T values were about square root of Q. So the second size not getting too big check should work out. Okay, so that's our construction. Let me try to give you a quick overview of why hiding holds. So the first part of our analysis will be to show that there exists a vector with very short entries, just entries in -1, 0, and 1, where Wi times C, for each bit I, there exists some vector C, where Wj times C is equal to the 0 string, is actually just equal to the 0 vector. And moreover, if you take that vector Vi times Wi times C, you actually get Q over 2. So, in some sense, the exact midway point. Okay, and we'll see in a second why this is important. Having such a vector is important. Now, showing this is actually not too hard. We can do it from kind of basic combinatorics, sort of pigeonhole principle type stuffs, and the fact that L is very big. So the fact that L is much bigger than M is important for just proving that such a vector will exist with high probability. The takeaway, though, the reason I'm interested in such a vector is that if we kind of add C in there, we have that Vi times C is equal to Q over 2, which will kind of essentially flip the valuation on the ith bit, but it won't have any impact anywhere else, given that a Wj times C is equal to 0. Okay, so to continue the analysis, we can now switch to a different generation algorithm, GenBits prime, but I'll argue that no attacker could informationally, theoretically tell whether I used the original GenBits or this new one. So in this new one, I choose T just as before, but I also choose some random bit B in 0, 1. And now my commitment is, instead of being just my seed, instead of just using T as the seed, I'm going to use T plus B times C. Okay, and then compute everything else the same way. Now, this distribution is very, very, very close to the original one, given that C has entry, that B is just a bit, and C has entries in just -1, 0, and 1, and the fact that T came from a relatively much larger distribution. You should only have negligible chance of noticing this different distribution. Okay, but so it's indistinguishable, so the attacker's advantage would be the same here, but the end effect is that whether B is at 0 or 1, actually doesn't impact the distribution of any of the proofs or the commitment. The only thing it does is just flip this bit R sub I after rounding. So here we essentially get information theoretic security due to this argument on the ith bit. Okay, so that's hiding mode. Now let's take a look at, that's hiding mode and the argument why hiding actually occurs in hiding mode. Let's take a look at binding mode. Binding mode, the gem bits and the verify algorithm would be exactly the same. And the only thing that's different is how I generate the CRS. And even that's very close to before. Steps 1 through 3 that I showed you will be identical to how we had them before. And anyway, the only thing that would change is how I change this vector v. So recall before, this was chosen to be uniformly at random, which was really important for establishing that argument that we just saw. And now it's going to be chosen as LWE samples. Okay, so for each I, we're going to have VI is equal to SI times AI, where SI is a random length n vector plus noise. Now, what we can essentially show in our theorem, if the learn with error assumption holds, no attacker can distinguish between the binding mode and the attacker node. One quick thing, I won't go into the details of this, but one thing I'll emphasize is that our hybrids are such that you can only change one V at a time. You have to first change the first one, and the second one, and the third one, and the fourth one, and so on. And the reason is that we have this correlation among the AJs and WJs, where AJ times WJ is equal to AI times WI for all I equal to J. So we can only pretty much we can only take one of these AI values at a time to be random, and the rest of them have to be chosen to make this relationship work. Okay, so let's look at the binding analysis. So suppose for a second that we're going to assume that the proof verifies and want to be able to show that there's hopefully only one way of, you can either open it to 0 or to 1, but there should be only one way of successfully opening it. Okay, so if a proof verifies, that means that AI times pi, the proof given, will be equal to the commitment. Okay, so here what we have is that the bit Ri will be equal to Vi times pi I, and then we'll do this rounding operation. Now, if we look at this bit, the first thing we can do is just substitute Vi with Si times AI plus noise, because that was how setup did it. Okay, then we can use the distributive property, just multiply things out. And what we get is that, remember that AI times pi I is equal to the commitment. Otherwise, verification wouldn't have worked. So we just get that the end result is SI times commitment plus this EI times pi I. And very importantly, EI times pi I is short because pi had to, or at least not too big, not all the way into Q. Pi I, in order to accept, had to be not too big, and EI was chosen to be short in the setup. Okay, so the takeaway here is that it really shows that if you ignore the EI times pi I, the bit only depends on the commitment and this vector S chose by CRS. So it seems to almost be almost determined only by the commitment and what came from the common reference string. The one little problem with this argument is this EI times pi I, which could, depending what they were, could flip it, possibly flip it to be a 0, 1. But this can only happen if the result was very close to the rounding boundary. So the way we can deal with this is that we just add an abort condition to this verify that if it gets too close, we just say reject, and anything that's not too close, these things couldn't flip it. Now, the rejection adds a little bit of a correctness error to our scheme. It turns out that there's some ways to deal with this where we can get back to perfect correctness, but I won't go into that for this talk. Okay, so finally to conclude and add a few thoughts. So we got the hidden bits model to finally work from the learning with errors assumption, which was the main result of this thing. Some active work that I'm working on with some colleagues is to be able to get things like transparent setup, where the setup could be just a random string, and we could get a smaller polynomial size modulus. Now, for some retrospective, we might try to say, well, why did this work and other approaches or other attempts in the past possibly didn't work? And it's a little challenging to figure out, what exactly happened. But one idea is that there was this RSA solution from the FLS 1990 work, where this common reference string publishes these images. The prover commits to a short function, and for which, and it can give inverses of these images. And I think maybe some previous attempts perhaps tried to follow this much more closely than this one does. This does use the hidden bits model, but doesn't quite try to achieve it in this way. And instead of doing that type of approach, it is more of like a joint sampling of a small commitment. There's not this idea of this function where I'm inverting it. Okay, well, thank you very much for listening to my talk.